Okay, this video is practice time. As we have learned so many Verilog syntax and say some code segment, it's time for us to do something valuable. Okay, this may be the first useful function block you designed in Verilog. Okay, let's say the specification. This module calls zscan. The function is for every 8 multiply 8 block, output the roster scan order in the order of zscan. Okay, let's first define what is roster scan order. So you can say this is 8 plus 8 block. Okay, totally 64 points. 8, totally 64. The number in blue color, this 0, 1, 2, 3, 4, 5, 6, 7, 8. We call this roster scan. From left to right, from top to down. Okay, this is called this scan. Sorry, this is called a roster scan. And for the number in black colors, we call it this scan. The order is something like you write the character Z. Yeah? Z. So in the Z scan order, the ID for this point is 0, 1, 2, 3. Like write the word, the character Z. Then we will use 4 small z to make the 16 point z. That is, yeah. Okay, so within each part, they are in small z order. So 0, 1, 2, 3, 4, 5, 6, 7. Then you come to here. 8, 9, 10, 11. Then come to here. Okay, this is the z order for 16 points. And this is the first part. The second part, yeah, the second part of 16 point. This is the third part. The third part of 16 point. This is the fourth part. So using the 4 parts of 16 point, we will build the biggest z. Yeah, we will build the biggest z of 64 points. So the number in black color is the index of the order. Okay. So what's the meaning of output the roster scan order ID in the order of this scan? Okay, let's say the waveform. Remember the black is this scan. Blue is roster scan. So the question is output the roster ID. So the output is roster ID. Okay. Output is roster ID. So this is the first one. 0. Then output 1. Then output 8. Yes. Then output 9. So the output is roster ID, but the order is in z order. So you have to use the z order to output the roster ID. That is the number in blue color. So 2, 3, 10, 11. So this point 16. Yes. Okay. Okay. So the block diagram for this block is clock reset. Then there is a signal to trigger the start of output. Then you will output 64 points with each cycle 1 point. Then you have a valid signal along with the ID data. So this is the defining of the input-output signals, and the reset is a synchronous reset with low active. So you can say this is a waveform. After reset, there may be 1 t-pulse of SOB. Then one cycle after SOB, you output the valid high and continuous for 64 cycles. Yes, from there, boom, 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 boom. Then 65 output the whole block. If there is another SOB pulse at the end of the block, so you will start the next output of the IDs, and it's also acceptable for there is a wait cycle between each block. For example, here the end of one block, so you have to drop the ID valid signal. Okay, drop the ID valid signal and wait for the next SOB pulse and begin to output. In this time, the value of ZID is unknown. Sorry, the value of ZID is don't care. You can put any value on the ZID, it's okay. Okay, this is the waveform. So there is a constraint that there is at most 1 SOF pulse for every 64 cycles. Okay, so you can't give SOB pulse at this place, at this place, at this place. Okay, and we call this waveform 2 block head to back. We call it back to back case. Back to back. There is no wait cycle between the 2 blocks. Okay. Then there is some design requirement. First, try to understand the function. Okay, do the right function as the spec says. Don't go to the wrong direction. Second, think about the algorithm and the hardware architecture. Do you think there is any algorithm for this function? Third, code it in sensible Verilog code and write test bench to test your function. So test bench may be something like that. This is you design this guy. Then you have to write something like TB test bench and give some stimulus to the DUT, such as you have to drive the clock, drive reset, and generate SOB, and you need to control the high pass of SOB. Yes, you have to obey the constraint. Yeah, you have to obey the constraint, and you have to make the case of back to back and some wait cycles, such as there is 1 wait cycle, 2 wait cycle, 3 wait cycle, 4 wait cycle. Yeah. Okay, this is what you have to do. And last, if we implement it in ASIC, it's assumed that if we use TSMC 113 nanometer cell library, the clock frequency should be higher than 350 megahertz. Okay, if you don't know what does this mean, I will explain it at the STA course. Okay, this is a course in several chapters later. So you can understand it as just try your best to shorten the data path, the combination logic data path for your design. Okay, this is the design requirements. So first, understand the function. Second, think about algorithm and architecture. Third, coding. Fourth, verification. Okay. Furthermore, if you can do this, it's better. Furthermore, try to automatically check the output of the DUT is right or not. That is, you can use your eye to check the waveform. Yes, cycle by cycle. 1, 0, 1, 8, 9, 2. Okay, you can check it cycle by cycle by your eyes. But this is inefficient. Okay, this will take a lot of time, and if you run the simulation several times, each time you have to manually check the result. This is very, very inefficient. Okay, so can you find some way to automatically check the output of the DUT? So to do this, typically you have to find two different solutions. One solution for the RTL for synthesis, and one solution for behavior model. Okay, you can use behavior model coding, and that is, the code is obey the Verilog syntax and can be simulated, but it doesn't need to be sensible. So you can use this one as a model, or you can say reference model or golden model, and we expect it bug free. Okay, we just expect it bug free. You can expect there is very little bug in this implementation, and for this implementation, there may be many bugs. Okay. So try to make the automatic check function in your test bench. And last, do you think there is any algorithm in this function? Maybe for some smart guys, you may come out very quickly of an absolute way of doing this function. Yes, such as you can think about something very simple. Yes, we have learned in the course, and maybe you will code it in some statement of about 64 or 66 lines. Okay. So, can you think from the view of algorithm? Can you find a better way of implementing the same function with PPA more efficient? Okay, just think about it. By the way, this function is a neat function in H.265 video encoder. So this is a useful function. Although it's small, but it's good for exercise, especially for beginner. Okay, thanks. Do it.